So, hi everyone. In the last session, there was a question that I was supposed to explain, and up to some extent, I have explained the same. But that question in details, I have uploaded in the solution PPT, right? So, I have elaborated some term. From there, you can get idea why the hydration energy was minimum in that case. I hope you have checked the solution already for the last week, that is week 9. Because total hydration energy, if uh, it is to be calculated, the contribution from cfse is there in the hydration energy. Okay, so in case of d5 orbital, cfse is 0. So that's why the hydration energy will be, actual hydration energy will be minimum in that case. Okay, in the case of metal having plus 2 oxidation state, you can observe the same case in case of manganese, because that is a d5 configuration. Okay, but there was a question in which it was given that Fe is having plus 3. Okay, so that is also a d5 configuration, so you can correlate it, right? So today I will be discussing assignment 10. Let me share my screen first. Okay, can you confirm please? Is it visible? Yes, thank you. So, I think, Doctor, you have asked the same question to repeat. So, have you checked the solution? Yeah. So, now that was clear, I think. Okay. So, today I will be discussing assignment 10 for this course. This week is related to some magnetic properties of coordination compound. Okay. So, these are the first two problems. Okay, so the temperature below which the antiferromagnetic substances behave as a simple paramagnetic material is known as Néel temperature, Curie-Weiss temperature, and inflection point. And second one, you have to identify which the complex of cobalt, in which case it will show the orbital contribution. Okay, I think you have already studied in detail about the when the metal will experience orbital contribution. Okay, so I will wait for 1 or 2 minutes, thereafter I'll explain. Okay, you remember that graph, okay, between temperature and chi. Okay, and one temperature, that is Curie temperature for ferromagnetic substances, and Néel for antiferromagnetic. So just try to give me the answer. For second question, what you have to do first, just write the electronic configuration and fill the electrons according to high spin and low spin, and also according to the geometry, that is octahedral or tetrahedral. And if you are getting the T2 orbitals, triplet degenerate orbitals in unsymmetric form, you will experience that the metal complex will show the orbital contribution, okay, in ground state. Okay, so first is A, right? And what about second one? Yeah, let me explain. Okay, so the Nil temperature of an antiferromagnet is the analog of the Curie temperature of a ferromagnet. Okay, so you can see after up to this temperature, that is Nil temperature, the substance behave as a antiferromagnetic material, and above that temperature it behaves at a paramagnetic substance. And similarly, in case of ferromagnetic, up to Curie temperature, it behaves at a ferromagnet as a ferromagnetic material. After that, it behaves at a as a paramagnetic material, right? Okay. So if I see the configuration, the high spin octahedral complex, okay, uh, it is a D7 complex, right? And on the ground state, if it is a high spin, okay, so the electronic configuration will be like this: T to the 5 and Ez2. And if it is a low spin complex, it will be T to the 6 and Ez1, okay. And similarly for tetrahedral, it is E4 T to 3. So you can see if it is T to 3, here you can see this triply degenerate orbitals are symmetric, right? And similar case here, sorry, similar here, that is also there is a symmetric configuration, but in this case you are getting the unsymmetric configuration in T to Z orbital. So that is basically creating the orbital contribution, okay. The high spin octahedral complex, that is this one, will be the right answer. And for the first one, it is also A, right? So moving to the next two, for this complex, there will be orbital contribution to magnetic moment from. You have to just identify whether it will be from ground state, first excited state, neither in ground state nor in excited state, and both ground state and excited state will create the orbital contribution. Okay, and second one, there is octahedral complex, metal complex with sigma bonding ligands, the set of orbitals that participate in sigma type bonding interaction. Basically, here you have to identify the symmetry, which basically in MOT, molecular orbital theory, or you can say the ligand field theory, which orbital of the metal involve in the sigma bonding. Okay, so the orbitals which are on along the axis involved in the sigma bonding interactions, and the orbitals which are in between the axis, they involve in the pi bonding interactions. Okay, yeah. So just try to solve. Here cobalt is in +2 oxidation state. Okay, so what will be the electronic configuration? It will be D7. Okay, and just you have to write the what will be the ground state configuration and what will be the first excited state configuration. Basically you have to transit from one electron from the ground state to the excited state, right? And check whether there will be a symmetry in the uh, T2 T2 orbitals or not. Okay, I think I'm getting the answer. Second A, first is B. Okay. Yeah, A is right because T2Z involved in the pi orbitals, right? Because the symmetry of this T2Z is basically matching with the T2Z of the ligand. Okay, because side by side overlap is there. And what about the first one? Just I'm going to explanation in the ground state. Uh, other criteria that you can follow while identifying the orbital contribution if the any state is having a triplet degeneracy. Sorry. So in the ground state, that is electronic configuration will be this. That is E4 T23. Sorry, there will not G. It will be 3, and you can see here T2 is symmetric. But in the first excited state, one electron is transiting from E to T2, so T2 will become unsymmetric configuration. So there will be no, so there will be orbital contribution for to the magnetic moment. Okay, so the first excited state will show the orbital contribution, and if I talk about the second one, as I have explained, that is these three orbitals basically involved in the uh, sigma bonding, right? And T2Z remain non-bonding here. But in case of pi bonding, T2Z remains the bonding one, right? So for an octahedral metal complex, that is the energy difference between the sigma, you can say Eg star also, and the pi T2Z antibonding will be considered as delta O, right? Octahedral crystal field stabilization energy, or you can say crystal field splitting energy when L is. So you have to identify if it is a pi donor ligand, it is a pi acceptor ligand, or both, or neither, or both. Okay, and the second one, the basic one, the property that can be measured directly using the Gauss balance. Okay, everybody knows the magnetic susceptibility can be measured. But what about the first one? Just think about it, and well, let me know if you know the answer, please. If you are familiar with the diagram of LFT of the octahedral complex in case of uh, pi, in case of this octahedral complex, okay, how the splitting is there, okay, and what will be the impact if it is a pi donor ligand or if it is a pi acceptor ligand. If there is a pi acceptor ligand, the larger splitting in the, because I am talking about the pi one, so splitting will be in the T2Z orbitals. So it will be very large splitting, okay, and EZ will be non-bonding here. So this gap will be large, right? And in case of pi acceptor ligand, this gap will be very less, okay. So what you have to identify for an octahedral metal complex, the energy difference between will be considered as delta O when L is, because in one case it will be the delta O between bonding and antibonding, and in one case it will be the energy difference between both the antibonding, that is Eg star and T2G star. I will show you the diagram, but before that I am very keen to know if you know the answer, please. So here is the explanation for an octahedral metal complex, right? It is a case of pi donor, and it is a case of pi acceptor. Okay. So here in the case of pi donor, you can see delta O is described as the energy difference between T to D star and T G star, right? So the option will be pi donor. But just let me explain. So for an octahedral complex, the energy difference between Eg star and T2G star will be considered as delta O when L is pi donor ligand. In a pi donor ligand, the SAC, that is symmetry adapted linear combinations of the ligand, are occupied. Hence, it donates the electron to the molecular sigma sigma star and pi pi star orbitals. So orbital associated to this easy orbitals are not involved in the pi interactions. Okay, because they are already involved in the sigma bonding. Okay, so here it will be as non-bonding, right? So apart, but you have to see here. Here it is pi star. Okay, so you can see the splitting here. That is T2Z and T2G star. There is large splitting when it is a pi acceptor ligand. Okay, so that's why this gap is also increasing as compared to this one, right? So the next one, in an octahedral complex, that is T1U and T1U star antibonding orbitals, molecular orbitals are obtained when this T1U ligand group orbitals combined with, okay, metal p orbitals. Just you have to identify the symmetry. Which symmetry is matching with this T1U group. Okay. Okay. Yeah. Right. And just calculate the magnetic spin only magnetic moment of the second one. First, identify the oxidation state of vanadium. What it will be. And after knowing the oxidation state, just write the electronic configuration, calculate the number of unpaired electron, and apply the formula, that is mu is equal to root n into n plus 2. Okay, so just tell me what is the oxidation state basically here. It is a complex of like this. So here basically the oxidation state will be plus 4. So it will be a D1 configuration, and just write the formula, that will be under root 3, that is 1.73. So it will be the right answer. Okay. Yeah. So in the octahedral complex, this T1U ligand group orbitals will have the similar symmetry that of metal p orbitals and undergoes head-on overlap, producing T1U and T1U star. That is One is bonding and other is undibonding molecular orbitals. And in the second case, I have already explained that oxidation state of vanadium is plus 4. So that will be the electronic configuration will be 3d1, and the unpaired electron will be 1. And applying the formula, that is root n into n plus 1 2, you will be getting this 1.73 Bohr magnetron as a magnetic moment of this complex. Okay, so this is the next one, the complex with spin only magnetic moment 5.92 Bohr magnetron will be. That is, there are three complexes, K3 FeCN6, Na3 F6, and K3 TiF6, and or both A and C. So simple question, just solve it by yourself and tell me the answer. Thereafter, I will explain. Just expand the, just calculate the electronic configuration after determining the oxidation state, and put the fill the electrons according to the ligand, whether it is a weak field or a strong field. Okay, and if you are getting five unpaired electrons, so you will be getting the value of this spin only magnetic moment close to this one, right? So anybody, if anybody is solving, please, I will wait for 2 minutes. So in the first first complex, that is Fe in plus 3 oxidation state, right, with the strong field ligand, right? And what about the second one? It is also Fe plus 3 but with weak field. And in the third one, it is titanium plus 3 with weak field. Okay, so what will be the electronic configuration here? It will be D5, and here it is also D5. And what about this one? It will be D1, right? So this will be not a answer. Okay, so let me fill these electrons since it is a octahedral complex, right? So if it is a this one, this ligand, cyanide ligand, it will be like this, right? And if it is a weak ligand like fluoride ligand, it will be like this. So unpaired electron will be 5 in the in this case. So if I calculate the magnetic moment, it will be around 35 or around 5.92. Second will be the right answer for this one. Okay, so here you can see the magnetic moment for all the complexes. It is also a 3d5. It is also 3d5, but in case of strong ligand, the electrons will be paired up, right? So the magnetic moment of this complex will be equal to this one, that is D1 configuration. Okay, because the unpaired electrons will be same in both the cases, but here in this case, five unpaired electrons are there, so that will be showing the magnetic moment of 5.92. Okay, So the next two problems in the complex, this carbonyl ligand, that is CO ligand, is stronger than this cyanide ligand. This explained by valence bond theory, MOT, LFT, and CFT. So spectrochemical series is basically explained by LFT, right? Why carbon this CO ligand is stronger than this one. Okay. So in the theory class, you have already studied in detail that which theory explained it. Okay. And what about the second one? According to ligand field theory, non-bonding orbitals are. Okay. So just if you know the answer, just tell me for the second one. You know the Eg orbitals involved in the sigma bonding, right? But these T2Z orbitals remains non-bonding. Okay. So just type in the chat box which options is the more appropriate for these two questions. Yeah. So first is C, second is B. Yeah. Anybody else? I have already given you the hint. Okay. So this will be the right answer. Okay. What about this one? The three set of p orbitals is designated by. You have to identify the term. Okay. You know the p orbitals are triplet degenerate. So here are three options. It is T1G, T2Z, and T1U. Okay. So just you have to identify whether p orbitals is a uh, zeroed orbitals or it is unzeroed. Okay. So basically, unzeroed orbitals are those who doesn't have a center of symmetry. And the second one is the group of orbitals responsible for s bonding formation is. Okay. Yeah. D and B. Yeah, right. Anybody else? Since p orbitals are unzeroed. Okay. So there is one option only which is saying that is T1U. Okay. Since p orbitals are triplet digit, that is Px, Py, and Pz, right? So this will be the right answer. And what about this one? S bonding, or you can say sigma bonding formation. Okay. So just rethink about the second one, because A to Z is also a singly degenerate orbital term, right? Okay, so easy will be the right answer. Okay, as explained. So how many types of orbitals may be seen in a imine bond of a SIP base? Basically, SIP base is a product of one aldehyde, okay, and amine. Okay, so this bond is just like this. Okay, right. So in imine, you have to identify how many types of orbitals will be seen. Okay, so because here is nitrogen and one is carbon. Okay, so sigma pi. Okay, and due to nitrogen there is non-bonding orbitals also because it is containing lone pairs. Okay, and what about the second one for orbital contribution in magnetic moment, which is the incorrect statement? First is orbitals must be non-degenerate to each other. They should have same shape. They should not contain electrons of same spin, or both A and C. So for, the first condition is orbital must be degenerate. Okay. Identify the two other statement whether they are correct or incorrect. Okay. Because in the D2 configuration, you can observe the orbital contribution also, but in case of D3, there is no. Okay. So it is not essential that they should not contain electrons of same spin. They would have same shape. I think that is not so necessary because they should be interconvertible. Okay. After interconversion, if any this electron is uh, transiting from one orbital to another orbital that is having the same symmetry, or you can say they can be interconverted. So electron, if electron is moving from one to another, that will be creating the orbital contribution. So they should be interconvertible, right? So the first one, for the first one, this will be the right answer, and for the second one, this will be the right answer, right? Yeah. So this was all about this assignment of week 10. Okay. So thank you very much all for attending this session. Yeah, thank you. I repeat that if you have any query outside of this these assignments, you can just post into the discussion forum. Okay, I will check once and respond to your queries. Right. So thank you very much again. I'm now closing the meeting. Thanks.